actions. So we have this definition of metapodicity. G act on X at a big space, at a big action. Is metapedagogic, M for short here, if for every isometric action. G on U, every G mount. Is essentially constant. And it's more or less the same as you can put a method structure on X, right? In a compatible way. But it's just making explicit what we mean by a compatible way with some measurable structure that we have. We've seen that the S2R actions on S2R U. U now is this guy, or on this guy. Is metapedagog. And so just pretty soon I will discuss, I will say something about all actions of semi-circular groups on metric spaces. But maybe I'll give one more example first and consider SS3 acting on, say, acting on modulo that guy over here. 1, 1, 1 with the X here, 0, 0. This is the sub. This is some unit and sub. So, can we put, so this would be my G here, this would be my X. Can we put on X? This is the question. This is any line. I mean, of course, I can put the 0 pseudometric. This is not a problem at all. Obviously, I can put a discrete metric as well, but this is not compatible with the measurable structure. So the question is actually, can we put a non-trivial one? No, non-trivial. So the answer is no. Here is why. So first of all, so I have the base point here. Now I'm explaining, maybe I'll not write down all the formulas, but pretty soon I will explain more general than that. But I want to do this example first. let me take this base point with the point stabilized by this subgroup, which I guess I'm belonging for myself U, and let's consider not the full SL3R action, but just the action of consider that block this is a copy of SL2. And this sits inside G maybe, eventually. Restricted to this block, to this subsystem. The metric must be trivial. Because it is a SL2 invariant metric on exactly that state. So it is, in particular, there is a point, or the base point, or maybe maybe I should say something because I guess I was about to write something which formally is incorrect. When I'm having a metric on a coset space, I can always view it. This is a general map. Any metric on G mod H, I can view as an H invariant metric on G. Oh, pseudo metric. We had the obvious map, the H invariant map, G to G mod H. Just the orbit map of the base point. Sorry, I'm having a metric here. Many times I'm just viewing it as a metric function, as a function defined over here. And when I think of a function defined over here, actually a metric function, as we used to do for maybe for discrete groups, I want somehow to think of every function, every metric, every metric on G is of course given by a norm function from G to infinity, satisfying the norm of the identity 0, the norm of x, the norm of x inverse, and the norm xy, that's the norm of x plus the norm of y. Well, the norm of x is then defined by the distance between x and the identity. Conversely, every norm, every such norm satisfying these properties, maybe I should call it a seminorm, right? Because this is norm is given gives rise to a left invariant metric. On G by, now I'm defining D. Using the norm. So just given this remark, in my mind I'm switching between the terms. A metric on, say, G mod H, and a norm on G, which is left invariant, which has this property, and also is invariant under the H action, the right H action. So thinking of this norm that I obtained on G using, I'm assuming having a metric here, I'm given then a norm on FX3R, which to begin with was U invariant, but now I see it should actually be SO2 invariant. So get S invariant. Back to the proof, but with our previous discussion. S invariant norm on G. That's SO2 again, out of block. In particular, the norm is invariant under the element, the subgroup, A prime, which is lambda inverse 1. It's a subgroup of G, which is actually a subgroup of S, by invariance by S, and I'm invariant by this one. And now I want you to recall the way we proved that every metric on that space is trivial. And this we did by the Mautner lemma, by contracting uniprotect using this. Do you remember? Shall I repeat this argument? I want just, I know that you don't need to know here, but I'm asking the others. Is it clear if any metric which is invariant under this one is actually the zero metric? Maybe I'll include. I think this is a cautious thing, and I will use again this idea. And then the metric or the norm is trivial. The norm may be viewed as a metric on G mod A is trivial, is a zero. So the norm. By the Mautner trick, which I'm recalling now. Again, this is exactly the way we prove the metric modicity of this thing. We will show that the point, or the base point, domain X in G mod A prime is also fixed. Or is of distance 0 from ux, u being one of any standard unit, u being, I don't know, of that form, or of that form, or of that form. Take u to be an elementary function, standard unit length, and I want to show that the distance from x to ux must be the same, must be 0, and this is indeed we can find for each such u. We can find sequence in A prime A n in n such that u a n goes to identity. So what is the effect? Let's record this. What is the effect of conjugating this element by that specific element? Just multiply alpha by lambda square, and then taking a sequence here such that lambda goes to 0, we'll do it. What is the effect of conjugating this one? Multiplying beta by to the power. The square came from, you have here the power 1, here minus 1, and this is lambda 0. The square is 1 minus 1. The power that you will get there is 1 minus 0. The power that you will get if you multiply the gamma here will be, I guess, minus 1 minus 0. This is related to things we did not discuss in this class, which is called root space decomposition. And those things that I was just saying, that minus that, etc., as the roots. But the thing is that they are never null. They are never 0, so we can always do that. And once we have this is the Mautner trick, is to look at the distance between x and ux. Then dx ux, well, we know that x is an fixed, so I can do that. This is for every n, and we know that the metric is invariant, so I can do this. Maybe I shouldn't have minus 1 here. U a n inverse is, which is, well, this goes to the identity. So this goes to dx, which is 0. So this sequence of constants tends to 0. Must be 0 to begin with. So all translations of it, in instance 0 points. And we see that the method is real. Okay. So this was yet another example, and now I want to make a theorem. let here be a metal space. Assume G acts on U isometrically and without fixed points. Then the action is over. You should remind what it means for an action to be popular. A map or a homomorphism. So a continuous map. A continuous map between the block of space, of course. X to Y is called popular. Definition. If, well, continuity is defined such that the pre-image of an open set is open. It always follows that the image of a compact set is compact. This goes without. I mean, this just follows the definition of continuity, but we want the other way around. If for every compact, this is pi, say, compact k inside Y, I minus 1k is compact X. This is one. Whenever we define a property of maps, we get for free a property of actions the following using the following pattern. If G act on X continuously, the action is called popular if the action map following G times X to X times X, Gx goes to X comma Gx is popular. I claim that stabilizers for proper actions are always compact. What is a stabilizer of a point? X in X. It's exactly the pre-image, well, the projection 2G of the pre-image of X comma X in here. So this is one. Proper actions. Stabilizer are compact. Point. Moreover, orbits are closed. To say that orbits are closed is to say that in the quotient space, X mod G, points are closed. So topology, the quotient topology is T1. In fact, more is 2. In fact, x more g is T2, is Hausdorff. So I explained this one, let me explain that one. I want to show that we need to show that the diagonal in x more g times x more g is closed. So I need to show that the complement of the diagonal is open. Oh, sorry. What I want to claim what is the diagonal in okay. Here is something that I should know. If a map is proper, then it is closed. The image of a closed set is closed. This is a proper map into a metric space, a metrical space. So the image of g times x here, in here, this means all the pair of points that are in the same orbit is a closed subset. Its complement is an open subset in x times x. So the complement is the pair of points which are not in the same g orbit in x. And if you project this from x times x to x more g times x more g, the map x goes to x more g is by definition an open map. So from x times x to x more g times x more g, the image of an open set is open. And I want to claim that the image of the set I just described, pairs of points which are not in the same orbit, is exactly the complement of the diagonal. So it is open. So the diagonal is closed. So that's practice Hausdorff. Okay, so this is just a standard thing that I want to review. So proper actions are always very nice. And basically, simple groups like SF2R or SF3R, the claim is they have only nice actions. Nice, all isometric actions of them are very nice. Maybe exercise. G act on X proper. X here is metrizable. Actually, it's a method. What we need for X metrizable, if and only if or maybe sorry, I will do it in Dutch and Conti first. Excuse me. X to y. Proper. If and only if for every sequence xn in x which has no converging subsequence, also pi of xn is no convergent subsequence in norm. So maybe you want to say that if you have a sequence that goes to infinity here, usually you use this term when X is locally compact, and which I don't want to assume here. But let's, between ourselves, say that such a sequence is a sequence going to infinity. If a sequence goes to infinity here, then it goes to infinity there. And I claim that this is homogenizable spaces, if and only if you have properness. Actually, for non-metrizable spaces, maybe I should say something. You want to replace sequences with nets, but then properness is not the right property. There is yet one more equivalent definition for the metrizable space, which is called, well, I said that a proper map is a closed map, which is rather easy to see. Actually, using this is very easy to do this. In fact, it is universally closed. Whenever you take the product, I take that map, pi from x to y, I can look at pi times identity from x times z to y times z. And this will be closed as well. A map with this property is called universally closed. And for metrizable spaces, this is the same as proper. In general, this implies proper, but it's not implied value. And this will be equivalent to that formulation using nets. Okay. So I will take this property in the definition of properness here and prove the theorem. Are there any questions so far? So I need to show that now G actually I will not prove the theorem in general. I will explain for maybe SL2R versus 3R. And we will explain what is needed to be done for other groups. Because I don't want to discuss this in general form, this root space decomposition that I was mentioning earlier. So I want G is SL2R, say, or SL3R, and I want to show that, well, let's say that G is SL2R. I want to show that this action, this isometric action, is actually proper. So G, and the map G times U that we see here should be a proper map. I would assume not. Assume G times U to U times U is not proper. That is, I can take a sequence tending to infinity here. I will have a sequence tending to infinity here that is not tending to infinity there. So it is a converging subsequence. So actually I can just restrict myself to begin with that converging subsequence. I have a sequence with not tending to infinity here, with non-converging subsequences there, such that its image here is converging. Now, to say that the image here is converging is, in particular, I will have a convergence in that coordinate, u. I will have in both. But the non-convergence will be then on the G level. This means that there exists a sequence Gn un with no converging but with UN, G and UN converging, say to x comma y. In particular, we get that Gn goes to infinity in G. The UNs do have a converging subsequence, so the G could not have. And now, since G is by assumption a Lie group, it is locally compact. I'm allowing myself to use the standard symbol of correct infinity. Now I'm using the following fact. Fact, G has a compact group K G is less than 2R, then K is SO. G is SO3R, then K is SO3. Actually, if G is SON, then K would be SON, such that G can be written as K A plus K for A plus being, usually A is denotes the diagonal group, A plus is the following. Maybe I'll write specifically for lesson 3. We write using this fact. Gn equals Kn, An, Kn prime. So again, the statement here, I should say explicitly, if you see this for the first time, so this is probably quite brief, but this is a very useful fact. Every element in actually GLN in GLN could be written as the product of 3 elements. First you take every matrix, every inverted matrix could be seen as applying a rotation, then a dilation. The dilation here is by rescaling the axis, each one in a different scale, and then apply a rotation again. So this is a geometric fact, and I'm using that fact. And somehow I try to write it down in a way that I explained for SLN, or for SL3 explicitly, but the way I wrote it down is valid for a general simply. Okay, so I want to take this here, bring that on.
What A plus is in the general setting?
Sorry?
What A plus is in the general
A plus in the general setting, generally, A is a what we call Tansabu. The maximal split semi-simple group. A maximal split
commutative sensible tensor group. And A plus, actually I will not use the fact that I'm doing for take an element in the restricted subset, not A itself. A plus is a standard group in A called Chamber. So this is about the general theory, which I'm not exposing now again. I thought that I will get to it, and probably we will get to it during the summer, hopefully, to how one should define it in general. But now, so I wanted to know that this could be generalized, but really think about this example in which everything is very explicit. Okay, so where are we? We have G, SL2 or SL3 acting on U. The action is by assumption non-Porter. So I'm having this sequence, Gn goes to infinity, Un converges to some guy X, and Gn times Un converges to some guy Y in U. The G's, remembering that this is a matrix group, I can write down in such a form, and somehow all the non-compactness in G. So, by the way, I should explain. If you see it for the first time, the group K, this is a subgroup. A is a subgroup as well. A plus is a subgroup in it. But this is none of these groups is normal here, so I cannot commute those. Okay. But somehow, when I view Gn goes to infinity, it happens because the eigenvalues here must go to infinity, or at least one of them. By passing to a subsequence, we may assume that Kn goes to converge by compactness of K. And now, let me do something a bit dirty from a notation point of view, replacing X by, I guess I want to replace X by K inverse. X and Y by K by Y, we may assume not only the X itself, all the XNs, YN, etc. Shifting before applying the elements G's, shifting everything by K, and after by K prime in an appropriate way, we may assume that maybe I should have written it more openly. Please tell me this in here. That Xn still goes to X. An Xn now goes to Y, and An goes to infinity, but now the A's are in A plus. So using this compactness, replacing things in an appropriate way, I can assume that my counterexample sort of, I'm assuming something I should not assume, right? I'm arguing my contradiction. I'm assuming something behave not in a nice way. This is the sequence G anyway. You agree, and somehow I pass all the bad behavior of the Gn, the fact that it goes to infinity, while those things get converged, I pass it to the A component of Gn. Is that legal? I mean, notation-wise it is not, but it's...
I'm not gonna go.
Thanks. Okay, but now we're in a position to do this Mautner trick that we started before. Now we get that alpha, beta, gamma, maybe n goes to infinity. This means hence alpha is the biggest. Alpha n goes to infinity in R. And the gamma n, actually what happens to this one? The product of those should be 1. So it must approach 0. And beta n does something as well.
Let it go to minus.
Yeah, positive effects. Sorry. I mean,
And now it's also set.
so if you have negative things, you can absorb into the case. So it must go to 0. Consider elements, consider the subgroup yes, I want to consider this subgroup. This is by notation. U was my metric space to begin with. Now let's consider this subgroup. Let's for n in n, if I take n and conjugate it by an,
And is a bad name.
and
And
and probably is bad as well. G. For G n, if you take this G and conjugate by an, recall what is happening. It's like take this number that you see over here, multiply it by alpha n, and divide by beta n. This is the effect of conjugation. So I guess I actually want to conjugate by inverse an. Then I will multiply it by alpha n that goes to 0, sorry, by alpha n inverse that goes to 0, and divide by the inverse part of gamma n that goes to infinity, and this will converge to 1. Now the claim is that this guy y over here, y is n in 1. And to see this, I will again use the same similar Mountain and brick. These we see again. And mountain. So actually, take G and N, and I will ask myself, what is that distance? And I will recall this is from you. I'm not.
In what metric?
Okay. So now I managed to erase the theorem. What are we proving? That if G acts on a metric space U, which I didn't say, I didn't tell you in advance, but the metric on U is called D, as usually metrics are called. D. Then the action, and if we don't have fixed points, then the action is proper. And this is what I'm proving. So I was assuming the action is not proper, and actually what I will show eventually is that we will have fixed points in the space. To begin with, I will show that we have a point which is fixed by something. And why is it fixed? So I guess that now I want to view this as the limit of a and x, and g, a, and y. With y and x. So yeah. Which is the limit of the a and x, g is a and y. And now I'm using the invariance. This is the limit of the x, sorry, x, comma, g, a, n, inverse, x.
Those should be x n.
Sorry?
Those should be x n's.
X, n. Thanks. Those should be x, n's. But in any case, now this goes to 1, and this should go to 0. And now, why we get that y is unfixed? Okay, so I guess I didn't. Previously, I said that SF3 is. I said SF3 acting metrically ergodic on SF3 modulo that. But up to applying conjugation-based permutation is the same. So, but we've seen that G add to G mod n, G mod n is metrically ergodic. This means every n fixed point assumption. Now, an negation assumption that exists a certain sequence is wrong. The clue that the action is wrong.
How am I saying this?
Minus 9.
-9.
Okay. Okay. So after taking a break, I'll explain how is that related to the heuristic.